Okay, I'm going to go over chapter 3, which is on isomers, degrees of unsaturation, a little bit on functional groups. I won't actually be talking about this in lecture. This will serve as the discussion of chapter 3, and you can read chapter 3 and try some of the problems there too. You're not actually responsible for this right now, although in chapter 7 you will be. I just wanted to introduce the idea of isomers. Iso means equal, mer, unit. So these are molecules that have the same formula, okay, but they're not identical. So they have different structures somehow. There's two broad groups, and I'm going to use C4H8 as our example. We have structural isomers, which have different carbon skeletons, or constitutional isomers. So if you look at the 4 carbons here, they're in a straight line. Here the 4 carbons are in the longest chain of 3 with a 1 carbon branch. They both have a double bond, so they're the same functional group of an alkene, but they have different structures. These are skeletal isomers. If I take away the pi bond and make a ring instead, which we're going to call degree of unsaturation, I could have all 4 carbons in a ring or 3 carbons in a ring with a 1 carbon branch. So again, they have the same formula, but different structures, so we would call these skeletal isomers. If I compare the cycloalkanes down here to the alkenes up here, again, they have the same formula, but different functional groups, so we call these functional group isomers. And these are sort of artificial divisions, but helpful for classifying our structures. There's a whole other group called stereoisomers, and chapter 7 is going to be all about this. Very, very big topic. These are molecules that have the same connectivities, but they have a different orientation in space. So if you look at these two molecules, they look pretty much the same on the left side over here. But when I get to the last carbon, this one goes up and this one goes down. So in this case, the two methyls are on opposite sides, which we call trans, or more commonly E. And if you look at these two methyls, they're on the same side, which we could call cis, or more officially, we call it Z. Okay, that's a little better way to do it. These are called diastereomers because they're not mirror images. Okay, they're different stereoisomers, but they're not mirror images. I had to use a different formula to generate the last category here. So if you look at these two molecules and think of this as a mirror plane, these are mirror images. But these molecules are not the same, they're different. Okay, and we call those enantiomers. So this is a very important concept, idea, but again, we'll talk about that in chapter 7. So I just wanted to show you some of the different types of isomers that are possible. Okay, for our first example of this topic, I'm going to look at the alkanes. Alkanes are super simple molecules. They only have carbon-carbon single bonds and carbon-hydrogen single bonds. Okay, so that's all there is. The very first one carbon, CH4, is methane, and this is one of the greenhouse gases that's so important in climate change that we have to worry about. So we might call this natural gas in terms of an energy source. But methane only has one way of being constructed. If I add in a second carbon, there's still only one way, and this would be ethane. If I add in another carbon, there's still only one way, and that would be propane. So this looks pretty easy. I mean, how hard can it be? 1, 1, 1. If I add in a fourth carbon, well, now we run into 2 possible ways, okay, which we'll see many examples of coming up. If I add in another carbon, we have 3 possible ways. We'll also look at that one. If I add in another carbon, 6, we'll have 5 possible skeletons that we could look at. Still looks pretty manageable. Not very many different structures for all those carbons. If we go to 7, it starts to jump up. 9, a little bit more. And if we go to 8, all of a sudden there's 18. It's a little bit hard to draw these, but I'm sure you could do it. When we go to 9, there's 35. Now it's getting pretty challenging. 10, 75. So challenging, but still possible. If we add 10 more to that C10 and make it C20, 366,000 possibilities. So it's really become impossible to generate all those. If I go up 10 more to C30, over 4 billion possibilities. If I go up to C40, over 62 trillion possibilities. So you can see it starts off easy, but by the end, there's so many that we can't even conceive of all those possible structures. And there's no reason we have to make them or draw them. It's just to show you the power of these numbers. So let's start with C5. So remember C5 right here? That was a pretty easy one. There was only 3 carbon skeletons. Okay, so we're going to take the three C5 alkane structures that's right here, straight chain of 5, straight chain of 4 with 1 carbon branch, straight chain of 3 with 2 1 carbon branches. Okay, and we're going to take one chlorine and replace all the different possibilities of hydrogen down here. Okay, so we'll see what that does. Now these all have names, and I've written them in here because our next topic is nomenclature, just to sort of get you tuned up for what's coming. You're not really responsible for them in this topic 3, but you soon will be. Okay, so pentane, butane, propane, and then we put the little side groups on. So now let's take those there's 3 skeletons that we have here, and we're going to put a chlorine at each of the different positions. So I could put it at the first carbon, or I could put it at the second carbon, or I could put it at the third carbon. Those are all different. So these are all isomers. Because I use the same carbon skeleton, we just call these positional isomers. Okay. This carbon here has 1 carbon attached. We call that a primary when that's the case. This carbon here with the chlorine has 2 carbons attached. We call that a secondary. This carbon here has 2 carbons attached. We call that a secondary. Okay, so now if we come down and use the other skeleton with 4 carbons in a row, 1 carbon branch, again, we can go down the line, put it at the first one, the second one, the third one, the fourth one. You'll notice the numbers change when I get to the end here. This is 1, and this is 1, because we always give the chlorine the lowest number when we count. But again, that'll be in our next topic. Okay, so as I go down, this carbon only has 1 carbon attached, so that's a primary. Notice this carbon has 3 carbons attached, so this carbon is a tertiary carbon. This has 2 carbons attached, so that's a secondary. This carbon has 1 carbon attached, so that's a primary. All right, and then if we go to the carbon skeleton where the longest chain was 3, all 12 positions around here are equal, so we could put it at any one of them. They're all the same, so there's only one structure when we substitute a chlorine on. Okay, this carbon right here with the chlorine has only 1 carbon attached, so that's a primary. But if you look at this carbon embedded in the middle here, it has 4 carbons attached, and we call that a quaternary carbon. All those terms will be showing up in our next topic. Now, any group that just makes 1 bond, like the chlorine here, is going to have all of these same 8 possibilities. So that could be a bromine, an iodine, an OH, HS, NH2, even a nitrile, carbon-nitrogen triple bond. There's only 1 point to attach. So they will all have 8 examples like I showed here. If we go to oxygen, oxygen's a little more complicated now because oxygen can make 2 bonds. So we have more possibilities. All right, I can make an OH, which only makes 1 bond. And I can do that the same 8 ways that I just did. Or I can put the oxygen in between 2 carbons. So if I put the oxygen between 2 carbons, we have to split up our 5 carbons. So I split it up into 4 carbons and 1 carbon, or 3 carbons and 2 carbons. So those are our 2 possibilities. Okay, so when we have a carbon on both sides of the oxygen, we call that an ether. Here I have 1 carbon and 4 carbons at the end, 1 carbon and 4 carbons chain, 4 carbon chain at the second position. Okay, here I have 3 carbons in, 4 carbons and 1 carbon, but this is the 3 carbon chain at the end, or the 3 carbon chain in the middle. Okay, and then I could also do 2 plus 3, but the 3 carbon chain can be connected at the end, or the 3 carbon chain can be connected in the middle. So these are all a little bit different, very similar. They're all ethers, and you can see ethers are very different than the alcohols up here. Any group that has 2 bonds can fit into these, what do we got? 8 plus 6, 14 patterns. So I could have an oxygen, or I could have a sulfur, almost identical, or I could put an NH. Okay, so the N has 2 different bonds to carbon. Now if we go to nitrogen, we can make 3 bonds, and so we're going to encounter the same 8 that we did the first time when nitrogen only has 1 bond, and in H2. Okay, the same as the chlorine, the same as the OH. Or I could connect the nitrogen at 2 places with carbon, so we call this a secondary amine. And again, we go to 4 plus 1. We could do that 4 different ways, or 3 plus 2. And we can do that 2 different ways. okay, depending if we attach at the end or if we attach in the middle. So you don't have to generate all these, and you don't even have to name all these right now. Although after we finish our next topic, these should be names that you can understand. Okay, so we're just trying to become familiar with the possibilities here. And then the last possibility that we did not have for the oxygen was we could make 3 bonds on the nitrogen, and so that's called a tertiary amine. So I could do that as a 1 plus 1 plus 3, and if I have 3, I could attach at the end or I could attach in the middle. Or I could do it as 2 plus 2 plus 1, and there's only one way I can do that. Okay? And that's the only group that we'll talk about having 3 bonds. We won't worry about any others. Okay, now I'm going to talk about degrees of unsaturation. Okay, some books call this hydrogen deficiency because some of the hydrogens are missing. If I have a carbon chain, there's going to be 2 bonding positions at every carbon. So in this case, I have 6 carbons. So I'd have 2 times 6 or 12 positions there. At the ends, I have another one on the right and another one on the left. So that's 2 more. So the maximum number of single bonding groups on this skeleton right here is twice the number of carbons plus 2. In this case, there's 6 carbons, so I'd have 2 times 6 plus 2. That's going to be 14 bonding positions. If I look at the formula of this structure right here, hexane, that's how many hydrogens we have. So this is completely saturated. You can't put any more groups onto this carbon skeleton. Now, if I come along and take 2 groups off next to each other and make a pi bond between them, then there could be 2 more spots I could bond something, but I don't have it bonded here because I'm the pi bond. So this is called unsaturated. This is a pi bond unsaturation. Okay, and every time I make a pi bond, I have to take away 2 groups. So every pi bond is going to make us come up too short. Now, if I'm calculating degree of unsaturation, I'd say I have 6 carbons. And so I look at the max. The max is 2 times 6 plus 2, it's 14. And then I come down here and I calculate the actual number of hydrogens, and I see there's 12. So I take 14 minus 12, I came up too short. Remember, there's 2 positions for every pi bond, so I have to divide this by 2. And I get 1 degree of unsaturation. In this case, it's a pi bond. But there's another way I can do this. Okay, I could go further down the line, take away a hydrogen from those positions and connect them, and that would give me a ring. Okay, so I could do it at 3, I could do it at 4, 5, 6. In this case, I did it at 6 carbons. Every carbon has 2 positions that it could bond. So if I look over here at the saturated 6, I have 14 possibilities, but if I count up here, I have 12. So 14 minus 12 is 2 missing. Divide that by 2, and I have 1 degree of unsaturation because of a ring, just like I had 1 degree of unsaturation because of a pi bond. So those are the 2 possibilities, rings and pi bonds. Now, if I look at some other atoms, the halogens, fluorine, chlorine, bromine, iodine, they all make 1 pi bond. They all make 1 bond, not a pi bond. So they count with the hydrogens. So I just have single bond groups here, and if I have any halogens, I'm just going to add them into the hydrogen count. All right. If I go to oxygen, oxygen turns out to be very easy. Okay, here would be an alkane, and I could take that oxygen and use one of its bonds to make a bond on the carbon on the left, and the other bond to make a carbon on the right, and you'll see it doesn't change the number of positions at all. It's a spacer, it just fits in between. I could do the same thing between a carbon and a hydrogen. It's a spacer, it just fits in. So no matter how many oxygens you have, you just ignore them. That's pretty easy. Okay, nitrogen's a little bit more difficult because nitrogen makes 3 bonds. So if I come down here and take this hydrogen away and use one of nitrogen's bonds to make a connection there, now there's 2 additional bonds. So there's the one that I took, but now I have an extra one. So every time I have a nitrogen, I have to add 1 more bonding position for maximum saturation for every single nitrogen. Right, so to calculate degrees of unsaturation, we don't know if they're pi bonds or rings because we don't have the skill yet to do that. We can calculate the maximum number of bonding positions very easily from the number of carbons and nitrogens. And then we count up all the single bonding groups, the hydrogens and the halogens, and subtract it. And then we divide by 2. And that tells us how many degrees of unsaturation we have. So maximum, if we only have carbon, no nitrogen, would be 2n plus 2. But maximum if we have nitrogen, and if we have oxygen too, is going to be 2n plus 2 plus the number of nitrogen atoms. And remember, add all the halogens in with the hydrogen. Count them all up together for actual groups that are bonded. So let's take a look at a formula right here, C4H8. So we know we're going to start at 4. Okay. These are the two 4-carbon skeletons. So we have a 4-carbon straight chain, or we have a 3-carbon chain with a 1-carbon branch. But these are going to have 10 hydrogens. So we're going to have to see how much unsaturation we have. So 2 times 4 plus 2, no nitrogen, so that's 10. Minus the 8, we're missing 2, divide by 2, we have 1 degree. So possibilities, we could have a pi bond, or we could have a ring. And these are the two skeletons that we could use to generate those possibilities. So if we look at pi bonds first, I could put a pi bond on the straight chain between the first two. So that's the only way I can do that. But in the middle two, between 2 and 3, I could either do it so that the methyls are on the opposite side, which we tend to call E, but can also be called trans. Or I could have the two methyls on the same side, which we tend to call Z, but could also be called cis. Okay? Now these cannot rotate back and forth between each other because we would have to break the pi bond. Okay, that costs a lot of energy. So these are stable molecules that are different from each other. And I could even do a double bond between 2 of these carbons up here. Doesn't make any difference. It has to be with the middle and one of the side carbons, and that would be different than any of these. So there's 4 different alkenes that have 1 degree of unsaturation. What about rings? Well, I have 4 carbons. I can make it in a 4-carbon ring, call that cyclobutane. But I could also make a 3-carbon ring and use 1 carbon as a branch. Okay, that's pretty strained, but still, it's very makeable. We can make that molecule. Okay, so there's 2 more. So our possibilities went up. Instead of the alkane, which only had 2, once we add 1 degree of unsaturation, we have 6 possibilities this way. What if we went up to C6? Okay, H12. Well, again, we start with the number of carbons, 2 times 6 plus 2, no nitrogens, so that's 14. Minus 12, so we have 2 missing groups, divide by 2, we have 1 degree of unsaturation, just like the previous problem. 1 pi bond or 1 ring. Now, how many ways can we arrange 5 carbons? Well, here's the alkanes. These are the skeletons. 6 in a row, 5 in a row, 1 carbon branch at number 2, 5 in a row, 1 carbon branch at number 3. 4 in a row, 2 1-carbon branches at 2, or 4 in a row, carbon branch at 2 and 3. Excuse me. Well, if we put a pi bond in, there's a lot of ways we can do this. Just on this one right here, we have all these possibilities up and down. The 1 position, the 2, 3, either E or Z, and the 3, 4, E or Z. So that's 5 different possibilities for this alkene, these alkenes here. If I go to this skeleton right here, do the same thing, go down the line, put it here, here, this could be E or Z, and down here, so 1, 2, 3, 4, 5. If I come to this guy here, I could do it at the end. This is a little tricky. I could put it between 2 and 3, but I could switch this guy over, and instead of the methyl facing the methyl would face the ethyl, so they're different. Okay, we'll call these E and Z, and then I could put it out here. So there's 4 ways. This guy can only go one way. We can put a double bond here, but we cannot put a double bond here because I already have 4 bonds on this carbon, and we can't go up to 5 bonds. For this one, I could do it 2 ways. I could put it any of the 1-carbon branches out like this, or I could put it between the 2 middle carbons like this. So there's 17 possible alkenes. Okay, what about rings? How many rings could we make? Well, we could put all 6 carbons in a ring, or 5 carbons in a ring with 1 carbon branch, or 4 carbons in a ring with a 2-carbon branch, or 4 carbons and 2 1-carbon branches, a whole bunch of different ways. And I don't even have all the ways here, because for this guy right here, it has a different mirror image, and I'm not looking at those right now. Those would be enantiomers. I could take a 3-membered ring and have 3 carbons left over, which I could put as a 3-carbon chain at the end, or a 3-carbon chain in the middle. Or I can split them up 2 and 1. I could do that different ways. Or I could make it 1, 1, 1. I could do that different ways. So if you look at all the cycloalkanes, there's 16 of those. If you look at all the alkenes, there's 17 of those. So our 6 carbons with 1 degree of unsaturation becomes 33 different possible structures, and we're ignoring the enantiomers. So that's quite a bit. It's starting to get pretty complicated. I would never expect you to generate all these possibilities, but I might ask you to compare, say, this one and tell me if they're the same or different. That would be pretty reasonable. Just for my own curiosity, I decided to go to C7, H14. So 2 times 7 is 14, plus 2 is 16. 16 minus 14 is 2. So again, 1 degree of unsaturation. Now, what did it become? Look at this. The last example we were just looking at looked pretty complicated. But now just 1 carbon more, and we've gone up to all of these possible alkenes, 35 of them, and all these possible cycloalkenes, 46 of them. So we have a total of 81 possibilities if I counted them all. Okay, I'm not even sure if I did them all. And again, I would never expect you to do this, but you have to recognize if these are different from each other, okay, and what the differences are. What if we had C4H6? What happened here? Okay, 2 times 4 plus 2 is 10, but we only have 6 hydrogens, so we subtract 4. So we divide 4 by 2, and we say we have 2 degrees of unsaturation. Well, this is more than we did before. So we could have 2 pi bonds, we could have 1 pi bond and 1 ring, or no pi bonds and 2 rings. Are these all possible? Remember, with 4 carbons, we have these 2 possible skeletons. So I could put using the straight chain, I could put the pi bonds on either end. Okay, this is kind of a special molecule, conjugated. So we call that buta-1,3-diene. But I could put the double bonds right next to each other, like this. We call that an alvene. Or I could actually put the double bonds between the same 2 carbons, and we call that an alkyne. And I could do that at the end, or I could do that in the middle. So these are all ways to have 2 pi bonds. That's all you really need to see right now, is there's 2 pi bonds. Now, could I have 1 pi bond and 1 ring? Well, I sure can. Here's a 4-membered ring, and I put in a pi bond. So this is cyclobutene. I can make a 3-membered ring, and with a 1 carbon branch, and put the double bond outside the ring, or inside the ring close to the 1 carbon branch, or inside the ring opposite the 1 carbon branch. So I have 4 of these where I have 1 of each. Could I make 2 rings? Well, this is pretty amazing. With only 4 carbons, we can actually make 2 different rings. Call this bicyclo-1,1,0-butane, which you don't need to know the name, but very, very highly strained, but it's been made. So this is not impossible, but it's highly reactive. So from our 2 skeletons up here with the 4 carbons and 2 degrees of unsaturation, look at, we made 9 possible isomers. So this unsaturation really increases the possibilities. So what I did here was I looked at a few other functional groups just to not only talk about unsaturation and possibilities, but also just to show you some of the functional groups. So remember our formula for complete saturation: 2 times the number of carbons plus 2, plus the number of nitrogens. Now we already looked at alkenes and alkynes, so let's take a look at acid chlorides. Okay, this portion right here is the acid chloride, and then you have infinite variety in this R group. This could be anything we want. Okay, well, what we're going to do is we're going to take 5 carbons like we've been doing, and just look at the acid chloride possibilities. So we take 2 times 5 plus 2, that's 12. And now single bonding groups are 9 hydrogens and 1 chlorine. So I'm going to take away 10. So again, I have 2 divided 2. I have 1 degree of unsaturation, and when we look at the acid chloride, we know that's a pi bond. So now what I'm going to do is I'm going to take these 2 4-carbon patterns and attach them to this acid chloride, which only has 1 point of attachment. I could attach on the end, that would be this guy, or I could attach in the middle, the 2nd carbon, that would be this guy. So there's 2 ways I could do that. Or I could take the 3-carbon chain with a 1-carbon branch, and I could attach on the end, which I did with this guy. Or I could attach in the middle, which I did with this guy. Okay, so there's 2 more possibilities. So just with this very simple formula, 1 degree of unsaturation, acid chlorides, I have 4 different possible acid chlorides. All right. If we look at this group right here, we have carbon-nitrogen triple bond. So we know the first bond sigma, and the second and third are pi bonds. So I know that there's 2 pi bonds here. It's got to have 2 degrees of unsaturation. But let's just double check. We have 2 times 5, 10, plus 2 is 12. But I have a nitrogen, so I have to add 1, so I have 13 possibilities for single bonding groups. I actually see 9, so I take away 9. I have 4 blanks, 4 missing groups, divide by 2, there's 2 degrees of unsaturation, and that's what we said over here, 2 pi bonds. So now I have the same 2 skeletons that I can attach at the end, or I can attach at the second position. These are going to be nitriles, okay? So we just need a little bit more to say exactly what they are. We'll learn that in our next chapter, chapter 4. Or I could attach at the one position here, like I did, or the middle position here, which I did, and these will be additional nitriles. So from this simple formula right here, and considering that's a nitrile, we have 4 possible isomers. Okay, now let's take a look at aldehydes and ketones. They're very similar to each other, and in most books they put them in the same chapter. So my formula here is C5H10O. So 2 times 5 is 10, plus 2 is 12. Take away 10. We don't do anything for the oxygen, so we're just too short. Divide by 2, we have 1 degree of unsaturation. And you can see in both cases, that's the pi bond between the carbon and the oxygen. I have the same 4 carbons, so I can attach at the end of the second position. I can attach at the end of the second position. But now with an aldehyde, I can only attach one way. So those are the possibilities. So the aldehydes are shown across here, much like the nitriles that we just looked at. But for the ketone, notice there's a carbon on both sides. So I'm going to have to split up my carbons. I have 1 here, but I have 4 more. And so I can either use that as 3 plus 1 or 2 plus 2. Okay, so in this case I did 3 and 1. But if I use 3, I could attach at the end, or over here I could attach in the middle, plus the 1. If I use 2 plus 2, well, they're both the same. So I can only do that one way. And so these are the ketones. So they look pretty similar, the chemistry is pretty similar, but not exactly the same. So aldehydes have the H here, ketones don't. Okay, these 2 groups are also kind of similar because they have a C double bond O and a CO. Okay, if there's an H at the end of the single bond oxygen, we call that a carboxylic acid. If there's a carbon at the end, we call that an ester. Carboxylic acids are a little bit acidic. You might think of vinegar. That's a carboxylic acid. And esters usually have kind of pleasant smells, smaller size esters. One that you're probably familiar with would be bananas. Bananas are something called isoamyl acetate, but a very characteristic smell. And so now you can see I have 1 carbon here, and if I'm talking about the acid, I have to put all 4 of my carbons on that side, as we've already seen at 4 different positions of the 4 carbon skeletons. But if I go to the ester, I have to split them up. So I have 3 plus 1 or 2 plus 2. But now it's more possibilities because I can put the 3 on the right side, or I can put the 3 on the left side. So I have more ways of doing this. So here I have 3 on the left and 1 carbon on the right, but I could do it at the end, or I could do it in the middle. These are different. I could go to 2 and 2, so that's pretty much the only way there. Or I could go to 1 and 3, but now 3 on the right here is at the end, or 3 on the right's in the middle. And I could even go down to no carbons to the side here, just 1 carbon, a C double bond O. That's called a methanoate or formate. And then I have all 4 carbons on the other side, and I can use the same 4 patterns we did up here. 4 carbon chain at the end, in the middle, 3 carbon chain on the end, and in the middle. And so you see there's a lot more possibilities now with these esters. So what do we got? 8, 9, and up here we have 4. So that's about 13. That looks good. And the last group we'll take a look at are the amides. There's other groups, but this is enough for us. So we're going to go say C5 again, H11NO. So 2 times 5 is 10, plus 2 is 12, plus 1 nitrogen is 13. Okay, and then we look, then you have 11 hydrogens, so we're going to take those away. We have 2 missing positions, 2 divided 2 is 1 degree. And that's our carbon-oxygen double bond. That's our pi bond. So now for the amides, we could have just one carbon attached to the nitrogen. That's called a primary amide. Right? And I could do it with the 4 carbons on the side, this way, this way, this way, and this way. The same 4 that we've seen many times before when we have a single bonding group. Okay, so there's 4 primary amides. If I go to secondary amides, it becomes the problem like the esters just above, because I can attach on the left and I can attach on the right, and I can do it 3 plus 1 or 2 plus 2. So here I have 3 carbons on the left at the end, 3 carbons on the left in the middle, 2 plus 2. I have 3 carbons on the right at the end, 3 carbons on the right in the middle on the nitrogen. I have 1 carbon, and I can do that 4 ways, just as we did with the esters. So again, there's 9 possibilities here. If I go to tertiary, that means I have 3 carbons attached to the nitrogen, and so I could do that as a 1 plus 1 plus 3. Okay, or I could do it as a 2 plus 1 plus 1. Or I could do it as a 3 plus 1 plus 1, and then the 3 could be at the end, or the 3 could be in the middle. Or I could do it as a 2 plus 2 plus 1. So you can see there's a lot of possibilities there. Okay, 18 I counted. So let's take a look at this final problem here, just to calculate a degree of unsaturation. So we start with the number of carbons, that's 19. So we take 2 times 19, that's 38. Plus 2 would be 40. But I look down here, I see 2 nitrogens. So I'm going to add 2 to that. So I'm going to have 42. Alright, that looks good. Now I have to count all the single bonding groups. I have 24 hydrogens, but I also have a fluorine and a bromine. So that's going to be 24 plus 2. So that's going to be 26. Okay, so that means I'm missing the difference between these two. So how many am I missing? I'm missing 42 minus 26. That's 16. But remember, it takes 2 to make a degree of unsaturation. So I divide by 2. I have 8 degrees of unsaturation. A lot of possibilities here. Pi bonds and rings. There are probably literally thousands of structures we could draw. Okay, but I just want to draw one just to see what it looks like. So I made up this structure here. Okay, so in this structure I have a ring, and I have a ring. So there's 2 rings. Pi bonds, I have a pi bond here, pi bond here, pi bond here. That's 3. I have 2 pi bonds here, 4, 5, and I have a pi bond here. That's 6. Okay, so that's our 8 degrees of unsaturation. And that's about all I wanted to get through on this topic here. So you can also read the book on this one, try some of the problems. But I won't actually lecture on this topic in class.